founder and CEO of Analogica Software Development Private Limited, Bangalore, and Satisure.com. He obtained his BTech in EC and MTech in Space Systems Engineering from MIT Manipal. He has worked with various DRDO divisions, ISRO divisions, Army, Navy, and Air Force for over 12 years, developing software for C4ISR, Spatial Temporal Information Systems, and data centric decision making systems. He has patented a unique fast feature engineering algorithm for feature extraction of time series data. He collaborates with researchers and academics across the world to develop new and improved prediction systems. He started Certisure in 2020, which is an ed tech platform focused on certification in emerging technologies. He is the recipient of the President's Award from Honorable President of India. So, with this brief introduction, I would welcome our honorable speaker for this session. Sir, please.
Thank you. So, thank you all. I hope I'm audible. Can you let
Yes,
me
sir.
know, Dr.
Clear, sir. Clear.
Yeah. So I'm Vijay Shantagiri, and so I'm really happy here. Happy to be invited to talk about my favorite subject, machine learning and deep learning. And I take joy in understanding these subjects, the internal, the way it works, how it works, and why it works the way it works. And of course, that's what we do. So I come from a technical background of electronics and communication. Then I moved to astronomy and space engineering because I was interested in these subjects more than because of some software development, coding, and everything was something we picked up easily, and I never felt that I wanted to. I wanted a formal education in software development. It's just you read books, you practice, and you get the idea. But however, I wish that I could, study more about the space stuff and control systems and navigation guidance and all this. And I think today, if I'm successful in machine learning and AI, it's because of the exposure to the mathematics involved in modeling of all these systems. Okay. So it's not because of my computer science knowledge that helps. It's because of the exposure to what maths and physics and how the whole embodiment happens in algebra and calculus of it. That is the takeaway. And so when we are going to talk about machine learning and AI and everything, I'll formally sort of go step by step. And I want to ask you a question, all of you, if Dr. Abdul can take up that poll. I would like to know, on a scale of 1 to 10, what is your exposure to machine learning and AI? Like, are you all familiar with it, or you want the advanced stuff directly, or do you want me to spend a little time trying to connect the dots from the basics? What should be my approach?
Participant can write in the chat box.
I would say A, spend time on basics. B, start from advanced. Okay, you can just type in A or B. If the more, I put the chat. I put the message in the chat next to you. You can all have access to it. And based on the audience input, I would like to structure the whole.
Yeah, dear participants, please see the chat box. Sarah has given some input like A, time on basics, spend time on basics, and B for start from advanced. Which one would you like? Based on your input, Sir will continue. We need some inputs, please.
Thank you. Thank you, Lakshmi ji. Thank you, Kara Sridharji, Gayatri ji, thank you. Yeah, bye Reddy ji. Yes, right. Right. So I guess I get the drift. I get the drift. I think it's best to start from the basics so that the story is continuous in terms. So let me just go here and let me just add another page so that I can start with the basics. I have to share the screen. That's one thing. So let me share the screen. So I guess the white screen is visible, sir.
Yes, sir. Visible, sir.
Okay.
Sir, if you could put the font little bit bigger, that will be beneficial, sir.
I'll do that. Let me just. Yeah, it will be bigger here. This is fine.
Yeah, fine, sir. Fine.
Okay, so let's start with machine learning. And the whole idea of this machine learning, if you think about it, um, so if you start from the beginning, let's say start from the core beginning of it all, so that it sort of gets your attention. So we have data with us. Data can be anything. Data is anything that you record when you observe something. Okay, you observe something and you collect the observation. And to collect that observation, we have created a language. We humans, we have created a language. We have symbols, we have sounds, we have numbers, right? All of these are fundamental units. So if you think about it, what world is this data coming from? This data will come from the world that we have created, the humans have created. Okay, so the humans have created the world based on our capacity to think, that is the brain's capacity. Okay, so if you think about it, what is the brain capable of? The brain is capable of feeling, and then it is capable of counting. Okay, these two things are bare minimum for the brain, and because these feeling and counting is in the context of time, because time is a function of the brain and time is not a function of the universe. Okay, other animals don't understand this time. We understand because we try to do everything in terms of time, because that's why we have 90-minute session with 30 minutes Q&A. Everything is in terms of time, correct? So we have already, our brains have evolved to feel, count and measure in terms of time. Okay, this is the given in the mind. We're not old models in terms of the evolution. Our new models, automatically everyone is born in this, with this context. So using the feeling and the counting and the knowledge of time, we take decisions. Okay, this is the given. You see the same thing what we have here. Okay, this particular thing. So back in 1943 to 1945, two legendary computer scientists, or you can say electronic engineers, mathematicians, everything, they're two legendary thinkers. One is Neumann, and the other one was Turing. Okay, Alan Turing and von Neumann. These two people, they decided that they will build a thinking machine. They will build a mechanical equivalent of the brain. Okay, that's the attempt. This was the agenda. As it said. So this was actually the agenda behind in 1943, 1945. That's what they wanted to build. To build this, then of course they realized that okay, how do you actually understand what the brain is doing? So they understood, okay, there's feeling, there's counting, there's time, there's decision. All these are observable entities. But then the inspiration for this came about when they started observing using those electron microscopes. They started observing how these cells inside the brain actually work. Okay, so you can see the neurons in our cerebral cortex are connected via axons. So these are fundamental units, the power sources, and they're all connected. Okay, this is how the brain works. A neuron fires, and this firing passes on another energy signature, and it fires another neuron. So each one gets fired. So if you think about it, when you look at a lion, you automatically run. But when you look at a small puppy, you automatically go and try to, cuddle with it and try to make friends with that dog or a puppy, correct? Now, why is it so that the moment you see a ferocious animal, you are on a flight or fight path? It is engraved in our memories. It is engraved in our genes. The moment you see a ferocious animal, you just want to run away from it. Does the same thing happen with a baby? A newborn baby, when it looks at a lion, will that also react the same way? Not sure. If the lion is peaceful, calm, then baby is also calm. But if the lion hears, roars, or makes a ferocious sound, then anybody would be afraid. Correct? Even that is engraved. So what is this engravement? It is a cluster of neurons. It is a cluster of neurons which is already programmed to give you signals, give us the signal, which will eventually help us to take decisions. It will trigger the field, and it will give the count. If the sound is just a small, a sweet sound, then there is no feeling that is triggered. If the sound is ferocious and it has a certain kind of pattern, which is in time, then the feeling is very strong, which will make you take the decision of running away. Correct? So this is how our brain works. So of course, at the very simple individual neuron, the layers of neuron connected in this way can yield a learning behavior. Okay, they realize this. This was already there. It need not be invented. The evolution had already invented that connections of neurons will yield a learning behavior. Now, trust me, there was no machine learning back then. They were very innocently trying to build a mechanical brain. So they studied it, and they finally realized that if you have to build a mechanical brain, then we have to build the mechanical neuron. That's what they thought. Of course, anybody would think like that, right? If you want a mechanical brain, I want this mechanical entity, right? So when they wanted to build that, then of course they realized all the other stuff, and they say, okay, there's a lot of processing that needs to be taken, and there's millions and millions of neurons that needs to be stacked in series and parallel, so that you have different contexts and everything. So finally, They built it, and today's world, what it looks like in mechanical terms is your GPUs. Okay, the graphical processing unit, not your central processing unit. Each one has its own central processing unit. Many of them clubbed together, many millions of them clubbed together, makes your GPUs, right? And so now they wanted to see this, the first artificial neuron. Okay, an artificial neuron fires, and NSEC here. If let me get in my pen that can write down. Could you all please type in one? Type in one if all of you are able to understand my way of speaking or the pace of speaking. Could you please type in one if everybody is following? Thank you. So that then. Okay. So an artificial neuron, what they said is it's supposed to fire, means it's supposed to transfer energy if there's a condition, if more than n input connections are active. Okay, this is the condition that we will set. We will set how many n should be there. We will set that condition. We will say if more than a certain number of input connections like this fire, then we will allow this C to get activated and transfer this energy to the next level. So if you want to really imagine this, imagine this. This is, see, I don't know if I have said, this is one neuron here, another neuron here. This is one neuron, and another set of neurons can be here connected. Then if that gets activated, it goes again, and this will also have a certain inputs. And if there is enough active energy here, then this energy gets transferred to something else, right? So there'll be connections of this, but they just wanted to build this one, the first one. That's all. Okay, they just wanted to build this one. So depending on number of connections from each input neuron and whether a connection activates or suppresses a neuron, you can construct now. So you can construct an and, or, and not logical construct this way. ANDing. If both of them, because you're all from electronics department, of course, so the basic electronics is all about the and, the or, and the not, right? So if you see, and in fact, ANDing, ORing, and NOTing is, these are the most basic logical gates that we have. And basically, they wanted to create this. They said, okay, let's just create this. And finally, this concept yielded them this. They said, then finally, they wanted to call this something. So they said linear threshold unit, LTU. And you can see, why would they call it linear threshold unit? Because it's linear in nature. It's not non-linear. It's linear. It's just from here to there, from here to there. No extra random or no extra stochasticity here. It's just, if it's there, you add it. Both of them add to and get to a certain level. We'll just, it means that if the weights here and the weight here means the signal energy. Okay, the energy of this and energy of this together, if it adds up, and if this is above a certain level, then we will sum it up, and then if it crosses a certain level, we'll transfer it. So there is a threshold. This is the whole unit, and this is linear in nature. So now you should think, what else would they call it? They can't call it Bugs Bunny or something, correct? So it makes sense to call it linear threshold unit. So add weights to the inputs. Output is given by a step function. Means this is where you interpret. Output is not given by a step function. This added weights will generate that step. If the weights are not enough to cross the threshold, there is no step. Okay, the step happens this happens, this stepping happens because of the weights, right? So it's all self-explanatory. So they just wanted to build this, and this, what is this doing? What is this doing is that now you have a series of electronic machinery wherein you have the control over the weights. This is a setup already. It's a mechanical setup. What changes here? Because you always in engineering, if you see, you respect the constants. Okay, that is, constants is nothing but the design. Respect the constants and control the variables. Okay, I mean, if you think about it, this is true even for life, right? The design is set. Then in the design of life, you see what are the variables, and then you become wise enough to identify which variable has to be controlled when, so that your agenda is met. I mean, if you think about it, it's a day-to-day practice that we have. We running a company, or we doing a project, we trying to get a, or me trying to make my wife happy. I mean, if she's angry or something, what has to be the constant. The design is like that. She's like that, and then I have to sort of not control the variables. I have to sort of mix and match the variables to finally, eventually, get the make the mood okay, right? So same way, all the machinery is also same. You set the design according to the agenda. Inside that, you have these variables. Now, these variables, the input of these variables, this is the learning part. Okay, when a machine learns, it starts adjusting these variables. Now we have to understand this. You still don't know this. I'm just trying to tell you that the whole learning, the entire learning, is about whether the machine realizes, whether the machine can understand what is the proper weight that needs to be given so that I get the final result. So what is the final result here? So we show the output here, desired output. We give the initial input here, and we say, boss, if you want to achieve this output, how much should be the weight for the scalar factor, which is the weight, that needs to be given to the input 1 and input 2 to get this output. So if it finds this weight, it means it has learned. Okay, this is the constant. This is the first round. In the first round, probably you may not understand, but we'll eventually understand it. Okay, this is all theoretical. When we start seeing it, you'll start understanding it. So the whole thing is a little deep, but of course, we will enjoy this whole process. Know this model. Get there. Now, what happens? Okay, once they build this, so you eventually, usually what we do, we add more of it. Okay, when we add more of it, a layer of linear threshold units now becomes a perceptron, something which can perceive. Of course, if you go about the word of perceiving something, it's a very perception is a very highly intelligent activity of a person. Okay, it's there, perceptions are there, but to have a perception, you need basically a little high intelligence. And of course, they were very ambitious. They said this simple thing can be a perceptron. Of course, now when you understand what perceptrons should be like, then you would say that this is very simple system of design to be called as a perceptron. However, they wanted a fancy name, so they got a fancy name, and fine. So you've got perceptron. What if you put a lot of perceptrons? You have multi-layer perceptrons. Okay, and then when you go and give it a depth, this multi-layer perceptrons, you try to give a lot of depth inside this, then you have a modern deep neural network. And this is your artificial neural network. Okay, because we say this is a neuron and this is a network of neurons. Correct? So this is your artificial neural networks. This is what it does. Fine. So far, I hope we've got some kind of a, in way. We started to dig in, we've started to understand what things are. Now let's come back, because learning, see, we are also you are also trying to learn now. Okay, you're also in learning process. So we can't learn just by me giving you one example, and I can't expect that you learn. Okay, we have 90 minutes where we both should sit, discuss, and eventual outcome of the 90 minutes is that you should have a perfect intuition, a working intuition of the reality of machine learning and deep learning. So we still have to understand machine learning, right? So now let me give you another parallel. So Neumann and Turing were trying to build this, and eventually, you know what they realized? They realized, okay, we have a theoretical understanding. So this is a theoretical understanding of how a artificial mechanical brain could look like, or an electronic brain would look like. Okay, back in those times only electronics was there, not computers. Okay, now they had to build the computers on it, right? So now they wanted to achieve this. So if you see the parallel of data structures, right? In computer science, there is a subject called, as a most important subject for computer science, is about data structures and algorithms, right? So before you come to algorithms, you have to understand data structures. That means in what fundamental structures will the computer understand? That is important. So you see, the feeling is a language, right? Feelings are all language. We use language to express feeling. So to express feeling, you needed to teach the computer what a symbol is. Means your language, your alphabets. It can be anything. If your vernacular languages, Kannada, Tamil, Telugu, and all those things have different symbols. Hindi has different symbol. English has different symbol. There is symbol, there is sound. Symbols and sounds together make language, right? Symbols, sounds, and knowledge and feelings together make language. So, but then for the computer, it has to be a symbol. So you put symbols. You tell it that hey, look, this is A, and then this is cup, and this something else is ma, right? Hindi. Of course, I only know 3 languages, so I cannot. So these shapes, you teach the computer saying, hey, when you get this shape, it's a language. But then there is another set of symbols, which look like this. This is also a symbol, but this can become an integer, a type. See, symbols now, these two in computer science becomes characters. Okay, and many of the characters becomes a string. And of course, many strings become sentences. Fine. The fundamental idea is the character. Now, this also can be a character. I mean, just because A. So can we do A plus A? Now, the A plus A won't make sense because it's not a number, correct? But 2 plus 2 will make. So you see, like this, going like this, they eventually decided that you have integers, then you have characters, and then you have many of these integers and characters becoming lists and arrays and all these things, and the whole data structure becomes more and more complicated. But the fundamental idea is from feeling, counting, and time. This is characters. Many strings become language. The feeling is covered by characters. Integer, numbers, that is your count. Together, using this, you want to do what? You want to do decisions. This is called your Boolean. Okay, so it has come from there. Then both Von Neumann and Alan Turing, they started working on a basic computer, right? A basic computer eventually has a control unit inside which there is a arithmetic and logical unit, right? And then you have your input, then you have your output, then you have your memory, right? This whole thing is control unit. Inside that, there is an arithmetic and logical unit. So now, this is the most important part. So you have to pay attention. What is this ALU doing? What is the most important work of this ALU? The work of this ALU is, see, this input comes from the real world. This real world has numbers and language. These numbers and language comes as input, but the machine is only designed to work with arithmetic and logical unit, because what it does is it understands binary, addition, subtraction, and, or, and not. Okay, that's all. Everything. Now, everything in this world, real world, numbers, be it language, whatever, will be reduced to an algorithm inside a computer where there is repetition. Okay, and repetition at extremely high speeds. That's what your computer is. Repetition of high speed and everything reduced to addition, subtraction, anding, oring, and not. How many of you agree with this? Or how many of you debate this? How many of you want to debate this? And how many of you agree with me? You can put a 1 if you agree with me, 2 if you want to debate. I mean, you type in 1 if you agree, or you can type in 3 if you don't get the idea at all. If you don't understand what am I trying to say here, I will make it clear. Basically, what I'm trying to tell you is this is how a computer works. Okay, I want you to understand AI properly. That's the reason. Because machine learning algorithms will not make this intelligent. This cannot change. This is the fundamental way in which a computer works. So that you know exactly where the AI, what is becoming intelligent is what you should know. This is it. This cannot change. So all of you agree with me that that's all happens inside. Addition, subtraction, anding, oring, and NOR. And NOR and OR is again another negative gate. So basically everything is, so you see addition, subtraction is all your integer functions and then your decisions. That's it, right? So now what has happened is the entire real world, when I feed in email, when I send an email to Sir, right? So that's my key. I put a text, I put a space, I put all this, the decorative way of writing an email with all stuff. And then it goes to the server, it reaches him and he reads it and so on. While going inside, it's all binary, going and everything, all this transaction that happens, everything is binary. So what we have been able to do as a computer scientist, a computer engineer, is we are able to convert this real world into a binary world. So that's your digital to analog to digital layer, which is the whole signal that gets converted to this real world. So everything, like you say, text to numbers and numbers to symbols, symbols to then binary. So this is common. This happens. Now comes the ML part. So now, parallelly, when you think how machine learning came about and everything, the same thing that we have here. I'll just take this. The integer and the character, right? This integer and the character can be taken apart and we bring it here. This integer and characters, we bring it here, and then comes your data science, the science of data, the fundamental understanding of the science of data, not the engineering of data, okay, not the computational aspect of data. You just say, how do you classify data? What kind of data do we have? So we have numbers, we have symbols, people give a lot of different theories. But the one theory which has remained very good understanding, very good approach, if you think, is you have qualitative data and you have quantitative data. Qualitative data is about and quantitative data is about numbers. See, so the machine is already equipped to do your data science. It can understand what is the qualitative aspect, what is the quantitative aspect. It already understands this. If you think about it, this is already there. Now what we needed was to look at the real world and in the real world, first attempt was to be able to uh, get those numbers in. Okay, so you have 1 and you have 2, you have 3, you have 4, you have 5, dot, 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 you have symbols, and you came with an abstraction, infinity. Then we said, can we sort of predict the nth number or something? So you got this En is equal to a plus n minus 1 into, correct? Right. So then you have this equation, which now given the common difference can predict what is the nth number. If you want the 50th number in the series, you can actually predict, because if you have the common difference here, then you can, let's say, an, or the 50th number that you want, you can get that by filling in those values. That's what your nth number means, right? Now, this is actually what you have done here is actually you have modeled the pattern. Okay, this is a linear pattern, something which what is the next number here? What is the 15th number? So fine, we've already modeled. What we did here is we developed an algebraic system. To develop an algebraic system, you have to evolve one step into the abstraction. So like this, next abstraction is, okay, look at these numbers in terms of set. Okay, so this is a set. Now, if you add this set and an operator with it, then together this is called a group, correct? So abstraction increases. I mean, that's what your mathematicians are there. They sit and they create more and more abstractions. Now you have algebra, you think a little different about algebra, then you start thinking what linear algebra. So like that, these things just go on, and that's when matrix came. Matrix is also an abstraction, right? Put everything in terms of a matrix, right? So if you have numbers like this is also an abstraction. These are all the whole of this. If you think about it, what is the end game of this? Why are we trying to do all this? Single answer to this is we are trying to model the pattern. Okay, we are trying to do this. So let me give you a simple example how the modeling of the pattern happens. Let's suppose we have okay. somebody's age and somebody's salary. Let's just make some fake data. Just plotting. Okay. So what I've done here by doing this, I have introduced a person who is around 10 years with a certain salary of, let's say, 10K. Okay. Then I've introduced another person who's around, let's say, 12 years, almost 11K. Then there's another person who's around 13 years, a little slightly higher. Then there's 14. Then there is another person who's again around 11 years or something, but the salary is high. So this is sort of how you connect this. Will you connect it like this? Would you like to connect this like this? No, we should not do that. We should go step by step, time wise, right? So you connect it like this. That's a sequence, right? See this? This is what I did. I connected this. Now this one, this is the model of this pattern. Okay. So this model, this is what I want if the machine gets this, if the machine draws this now, then the machine has learned. Means, but what is this drawing? This drawing, okay, let's suppose this age is X and salary is Y. So what I want is a function. What I want is a function expressed in terms of X and Y, which will give me this model. Means what? Some Y is equal to some X cube, 3X cube plus 2X squared plus 1X plus C. Okay. Now this, I'm just giving, I'm not saying this is that. I'm just giving you that this equation, okay, this equation should give me this shape. How? X is input, Y is output, correct? So if I start putting 10 years, something happens and I get a Y. So for 10, I get a 10 here. Then for another 11, I should get another Y. So I put that Y. So I want this equation to be in such a way that I get this curve back, or at least I get these points back. So basically, I'm asking the machine, look at my age and look at the salary. Okay, somebody's age is like this, somebody's salaries are like that. People whose ages are like this, their salaries I have plotted. Now, why don't you go ahead and tell me the equation which governs this pattern? So the machine is going to find this algebraic equations for you. And whatever you're seeing, this 3 and 2 and 1, you see, randomly I put 3, 2, 1, or it could be something else. It could be, it would be 5.7x cubed plus 7.2x squared minus 9x minus c. So what is this? Plus and minus suddenly 5.7. These are these. What could this be? These are your weights. And then there is something, a new term that gets added, bias. Okay, where is this bias? The bias is this, weights and biases. Okay, we're just adjusting so that we get that appropriate Y for a given X, so that your X's and Y's series of this, because see, what is this? This is all X and Y, right? Many X and Y's, correct? This is one X, x1, y1, x2, y2, x3, y3, x4, y4, which means what? For every x, there is a appropriate y, which becomes the point. Correct? So now I want the machine. We have devised a way in which the machine can give me those, give me the equation, general equation, wherein I can get these x and y's. Is the concept clear? Can you type in 1? I would like all of you to participate, at least a measure of people to be able to tell me, give me a 1 if you have understood so far, and 2 if you want me to repeat this. Oh, okay. None interest. Anyone
Dear
has any
participant,
doubt?
yeah. Yeah, dear participant, you interact, that will be better so sir can understand whether you are understanding or not. Okay.
Okay, following. Anyone has any question at this point of time? Any doubts here? You can unmute and talk if you want to talk. Anyone has any doubt or anything? Then if not, then I move ahead. Okay. Right. So basically, this is what I want my machine to learn. Now, how will the machine learn this? Now, that's the question, correct? Basically, what you just saw was a linear regression. Okay, I guess all of you are somehow familiar with this. This is a linear regression model. So all this linear regression is finally you. In fact, we don't build a model like that. That this model that I drew for you, that we can build a model like that. I mean, it's not a problem. We can build a model like that. In fact, let me show you a certain model which looks like that. Do you see this? This is a pattern, okay? And I was trying to fit the red color line in the model, and red color line came because of this equation. The machine thinks that this particular equation will generate this line. So it does. I mean, that's it. It has. But I have said, I have given it a degree of freedom 3. Now I can actually go and so this is another interesting. So here also I've given a degree of freedom 3. I can change this. See here. See this. This is a scattered point. Okay, scattered point. If I give this degree of freedom, more degree of freedom here, say suppose I give degree of freedom 7, what it will do is it will try to fit all these points if it wants. I have just said 3. I've just said you give me minimum degree of freedom. I'll say I will give you only 3 degrees of freedom. Max in that 3 degrees of freedom, get the maximum points within your range. That's what I'm telling the machine. So I said, okay, fine. If you only are giving me 3 degrees of freedom, then I'll do my best and it will fit like this. Now, if I change it to 7, you can just see if I run this program. It became a very big equation. You see this? Earlier, it was a small equation, which looks like this, a 3rd degree equation. Now it's a 7th degree polynomial. Let's see what is happening. It has tried to go everywhere, and I think it is still taking time. Yeah, we've got it. So, and of course, your accuracy and everything increases large. But now you said, okay, this is a seventh degree polynomial. You can go as much as you want, but then every time trying to predict using this will take time. Correct? So you also are looking at the practical aspect of building a machine learning model, saying, okay, would you like to be, 100% right? If you want to be 100% right in your prediction, then you will have to wait for 5 minutes for that answer. Or it'll say, okay, if you want to be 85 to 88%, right? Then you only have to wait for 0.3 seconds. So then we do a trade-off. We say, okay, if 80%, or if I'm okay with just predicting getting 90% accuracy, I'm fine. And there's one more problem. If you try to get 100% accurate models, now the key aspect is, if you try to get this 100% accurate model on this, okay? So what we call this, if I try to use this data into a machine learning model, let's say a linear regression machine learning model, these green dots are called as my training data. Means the data used to train the machine learning model is called the training data. So on the training data, you suppose you go and build up, because you have more computation power, you go ahead and build this amazing model which has covered everything. But the reality is that this model has to perform not on training data, this model has to perform on the real world data. In the real world, for some real X, I want to get the best possible prediction of the Y. So if this machine has learned, it's like this. You have forced the machine to learn so deeply. It's, how do I say it? You have your kids, okay? You have your kids. Do you want your kids to just sit and read the book from morning till evening and no other extracurricular activities? No games, no interaction with students, or no going out, no adventure activities, no workout, no physical adventures and all this. Would you like it? I mean, of course, and then no eating outside, only being in AC, only drinking boiled and cooled water all the time. Would you like to do that? You don't want, like, you want a kid who is ready to adapt to the real world. Why? Because no matter what kind of environment you're giving in your house, you know that the outside the house, things are not in your control. So you want a kid to be able to adapt to the external environment, right? So that's exactly what you think of your machine learning model as your kid. And don't try, and this green dots that you are able to collect is your house. So you don't want to build a model thinking that whatever you have collected is the ultimate answer, because the reality could be very different. So I would rather build a model. I would rather build a model which looks like something like this. This gives better accuracy in the real world. It may not give you good accuracy in the training data. In the training data, the one which went like this was 100%. But this one probably will be around 80%. Let me try that other one. So something which goes like this. This blue can be 100%. But this blue, which is 100% on training data, will probably give only 50% accuracy on real world data. But the red one, which is giving 80% on training data, might give you 80% on real world data. Right? So that's what the trade-off is. So you're trying to do a bias variance trade-off. That's one of the aspects, the practical aspect of building a machine learning model. So now we have to go back and understand building a model is what we, as we discussed, building a model is about building this algebra or modeling the pattern using the algebra, or it is an algebraic pattern modeling mechanism. That is what machine learning is. Okay, that's why it's called algorithmic learning. There is an algorithm which eventually develops the algebra whose work is to model the pattern of the data. So think like this, right? So, so moving ahead. So you have all this training data, real data, and everything. So Abdul sir, may I ask you, is this lecture being recorded?
Yes, sir. Recorded, sir.
Yeah. So you shared this copy of recording with me for future reference.
Okay,
Right?
sure, sir. Sure, sir.
So now moving a little further ahead, we have these machine learning models, which are just nothing but algebraic relationships that you're developing between the input, which is here in this case as age, and output, which is your son. Now the problem, this is a simple problem. This is too simple a problem. In fact, this was a part of statistical learning, because mostly all this is statistical learning. And we had one more thing that we discussed that we will do. Let me see if I can copy this again. So we were discussing how will the machine develop this model, right? We were discussing that. So what the machine does is very simple. It's an algorithm. So it will just be here. It'll start from here, and at this, and then slowly it will move up. And every time this moves up, basically, let's say this is a. It's not. Let me explain. Let's suppose we want to put a straight line. The equation of a straight line is nothing but y is equal to mx plus c. This is a general equation of a straight line. The more degrees of freedom, the more degrees here. Okay, that's how it works. M is your slope. So that slope is nothing but, this m is nothing but dy by dx. It's very important. It's not technical. I mean, there's no fancy way of learning this. Eventually, everything comes to technicality. That's what is working from inside. Once you know how it works from inside, then everything is clear, right? So that's how it is. You can't avoid it. So sorry if we are getting into the technical aspect of stuff now. Okay, let's say this is dy by dx. What is this dy by dx? That's dy by dx is the ratio of the change in y for change in x. I mean, for how much change in x should I do to get a change in y? That's what this ratio is. So if you say settle at this level, this pattern, and then you say I want to do a dy by dx of it. Right, so this is properly, if you see, if I set this up here exactly, don't you think almost everybody will agree that I'm almost at the center, exactly at the center? You see, half of it is here, half of it is here. So your dy by dx is almost equal to 1. is because this much if I move, this much unit if I move in X, this much unit I'm moving in Y. So almost this is a direct linear response. That's why it's called linear regression, a linear straight line. Equation of a straight line, the linear equation is y is equal to mx plus c. M, if it is 1, then you have, if m is 1 and c is at 0, because this c is here, wherever it is cutting this, the c is here. So then it becomes what? Y is equal to x. Means whatever is x is, that much is y. So it's a straight line. So we build on this. Now we say, but not all data will be like this. We want this model. Now, what is the agenda of this? I want this straight line to set itself up in a position where maximum numbers are around it. So I did this, correct? Now I did this. I only set it up. If the machine is able to set this line, then machine has learned. That's it. Okay. Now, very simple. It will start from here. It will start from here. And at this level, what it will do is it will just calculate the distance of each point, the orthogonal Euclidean distance. Orthogonal straight line 90 degree, Euclidean is Euclidean distance, right? Root of x2 minus x1 plus y2 minus y, right? Root of that square. So that is your Euclidean distance. So it will set this here and it will keep a note of it. Then it will increase. Then again it will calculate. Then it will increase. Then again it will calculate. So it will keep on calculating until the sum of all these distances, called the sum of squared errors. The square root of the sum of all is minimum. So it's an algorithm. Anybody can write this algorithm, correct? It's an iteration, right? So I told you, everything gets reduced to addition and at repetitive high speeds. See, I'm still in that, within that scope of what a computer can do. It is just that we have reduced our problem to an algebraic problem and then use computer to repetitively do something. So all machine learning algorithms, internal gist is, are you able to see your machine learning problem or a real world problem as an algebraic problem, right? So you want to solve that algebra. You know intuitively what that algebra is. Now you want the algorithm to develop that algebra for you. So that's how it is. So eventually it is going to come here, settle down, and it will also shift this like this. Okay, shift. Once it will try here, come here, it will see it is fine. Then it will start again. Second time, it will come here. Then it will do everything. Then it will come here. Then it will do everything. So instead of doing all this step sizes, second step, third step, fourth step, fifth step, sixth step, and all this. So how do you decide? How do you decide that I have to go step by step like this? You see, first step you'll come here, second step you'll come here, third step you'll come here, fourth you'll come here, fifth you'll come here. That is fine. What if your step size was like this? What if you start here? Then second, you see this distance here, then you'll end up here, then suddenly you'll end up here. But you missed that line only, right? So what we want something which looks like this. Let me give you another. We want the step sizes. Let's say first step size, let it be like this. Next step size, it should slow down. Next step size, it should slow down. Next, it should slow down. Next, it should slow down. Sorry. Then it should converge here. Do you want this or do you want this? Which one is more intelligent? This one is more intelligent, right? But this cannot happen unless there is a feedback. Your first step, it came from here to there, from here to here. Then there is a feedback which comes in saying, okay, this much has happened. Why don't you go slow next time? Why don't you go slow next time? Now this aspect. Anyone who wants to tell me what it is? Anyone who knows this? What algorithm is this? GD. Anyone? It starts with G. Okay, let me give you a hint. Somebody who knows machine learning and AI will tell me this. So somebody who's got even the faintest idea. Okay, let me give another hint. Now, gradient descent. The descent or the ascent, whichever way you want to call it, there is a gradient to it. It is not just shifting like this. It goes like this, then slows down, slows down. There is a gradient to the descent itself, right? So every machine learning algorithm, be it deep learning algorithm, eventually has the optimizer of that function, which has gradient descent algorithm in it. This is the backbone of all machine learning algorithms. Okay, so what is this now? The starting point. That's the hypothesis. From this hypothesis, there's a feedback. The feedback eventually measures something. Eventually, you start giving it that push, and that's why it is the weight. How much weight? And now, because I am trying to move like this while this is fixed, you see this, I have fixed this. Think about this as a fix. Because it is fixed for this particular movement, that's why m into x. But because I have to shift it whenever I want, I have to shift the whole pivot, that's why it is plus. The shifting stands for plus, and m into x. Why is it not m plus x plus c? It is m into x because it's a scaling factor, plus c because the c is a bias, which comes later. It's like you find out that from here, you find out that this is the correct line, but this is correct only when you shift it like this. So it will find that it will think like this is how the algorithm thinks in terms of the weights and biases. It will eventually get there, and then you get one small equation for this, and everything is easy and fine. Right? That's fine. You get the equation, and you successfully use your linear regression algorithm. However, what if your equations or your problem statements are like this? See, now we have x, we have y, we have z. And this is not just it. You are dealing, sometimes you deal with 35 to 40 columns, okay, out of which one of them will be a output, and rest all 35 to 36 or 40 or 50 variables will be your input. Now you want an algebra. You just saw the algebra, the complications of the algebra that we just built here. See this? We saw the complication of this algebra, and what we're trying to fit x and y only. There's only one x, there's only one y, degrees of freedom 7. The equation look like this. Okay, imagine 40 different x's, which looks like x1, x2, x3, x4. And what will be this x1, x2, x3, x4? Let's say your y, let's say your y is for example, what we saw in the missile hit right now. Okay, so there were a lot of missiles coming in, and whether to engage or not, or hit or not, because every missile it can't engage. Once it engages, it has to hit. If it is not intelligent enough to identify a target, then it will not take off. Then see how this whole thing is working. So inside that there will be many parameters: radar cross section, speed of it. Inside that there will be many image processing parameters. Like that, there will be many parameters. The output is, should I launch or not? Once launched, then again another algorithm takes over. Okay, because it is also moving. The radar is giving feed to the missile, so fine, it will have to eventually go and get hit, right? So like that, there'll be many parameters. And of course, I was just listening to the creator of the Akash missile system. Was on air today. I think he was from Andhra Pradesh, Prahalada or somebody, right? Ramarao. So he was saying that they actually delivered this Akash, this system, in 1987. They delivered it, and I think by 1995 or something, it was already inducted. So we are looking at a system, I think by 1989 or 2000 it was inducted. 25 years ago only this whole system was inducted. And this will hit a proper trajectory, projectile can be easily measured. If something moves like this, and it has to become more intelligent, and this actually is able to do it. So back in the time, all these are old stuff. Only it is coming to us today because our computers have become very sophisticated now, so we are able to solve all this. Otherwise, old computers, we can't even get one problem solved. So I mean, what I'm trying to get at is, when your parameters are very, very, very large, input parameters, you can't even imagine in terms of x and y, because you want x, y, z. Now what happens? It's not x, y, z anymore. It's x1, x2, x3, x4, and I can't even draw it because it doesn't make sense. It's like, okay, if you take this as y, you have all these. In fact, it should not be drawn like this. Okay, this is not in one dimension. It is its own dimension. You can't even imagine it. So what do we do to get this solved? We convert this entire Cartesian coordinate system into a linear algebra coordinate system. We convert that entire thing into linear algebra. We linearize the whole thing, and that's why linear algebra is very important. So now, when this high level of machine learning algorithms are required, or data set has to be a high level, high dimensions of data is given to you, then your normal machine learning algorithms won't work. Now, so we need deep learning for it, right? So what was the takeaway from machine learning? Machine learning, we were trying to model this algebra, right? That's what we do. Yeah, this is just remember this. The algebra of the pattern is the model. The model is nothing but the algebra of the pattern of the data, pattern between input output, both that you should see and get to the algebra. So can we say, but what did we get finally? What was the end result? The end result was a function between input and output. Agree with me, all of you? Right? So can we say that machine learning algorithms, there are many, but eventually everything is a local function approximator. It's a local function approximator. Means it's a function approximator. That is what your algebra is. Function is an algebra. It approximates what is the function which models the relationship between A and B, or the function input and output, which is local. Correct? So that is fine. But what you want? You want a universal function proxy. This is what we want. Fine. So when we want a universal function approximator, shall we take a 5 minutes break or something?
Yes, sir.
I think we are exactly.
You can take break, sir. Yeah, fine, sir.
Yeah. So when I come back, so I have something very interesting. When I come back, we'll have something more visual to play around. So all of you can just go here. The 5 minutes, or let's say we come back. Let's say at 3:25 or something, 9 minutes. By that time, Just Google this playground.tensorflow.org. See, what do I want? I want you to Google play. Okay, I just copy this video, send it to you in the chat. I want you guys to open this. Let me close this. This is what we want. This is where we are going to study the deep learning. Okay, so let me put the same thing in the chat. Of course, deep learning is actually a very deep subject. I mean, but given the time, I think we'll understand this. So we're going to come here. We're going to understand that artificial neural network is a universal function approximator and not a local function approximator. But good thing is that you understood my context of what an approximator is, what an algebraic approximator is, and local algebra. We've understood that. We'll catch each other at 3:25, whatever the time is, 7 or 8 minutes. Take a break, water up. I'll also do the same thing. Let me give my vocal cords a little rest, and I'll come back at the same time. Right? So I pause this by that time, and the moment I come back, that.
Sure, sir. Sure.
Hello. Sir, am I audible?
Yes, sir. Yeah. What do you guys?
So shall we start?
Yes, sir. You can start, sir.
All right. So now in machine learning, some key aspects of machine learning algorithm. Two important aspects: feature extraction and feature selection. Okay. So feature extraction and feature selection is very important when you have to decide between inputs which has a large amount of parameters. Let's say I talked about 40 parameters, and then there is output. Okay. So when you have so many parameters that needs to be selected, you don't want to select all the 40. I mean, maybe all 40 need not give you the right model. Suppose you have, going back to our previous example, so we were just here, right? We were, so we were looking at this, and we had age and we had salary. Yeah. Suppose you have the degree of a person. So think about it: age and which degree? A degree of a doctor degree and a person who's got an accountant degree. Okay. Accountant versus doctor. So in this data set, there could be doctors, there could be accountants. So a doctor probably will have high salary at mid-age, but then an accountant, even at higher ages than the doctor, could still have less. Like this, let's have another parameter of how many liters of water a person drinks. So once we see this, we'll realize that how much water a person is drinking will have nothing to do with the salary. But somehow we have still collected this data. What do you do? It's been given to you. We have collected all this data for you in the 40 parameters. So now the machine learning model, we manually will have to say that, hey, don't use this parameter at all. We don't want this parameter to be used. In machine learning, we have to do this manually. We have to select the feature and we have to engineer the feature also. Sometimes we take, there will be many parameters. So we'll just say 3 parameters, we'll club them together. We'll add them and make a 1 parameter. And we'll use this as the, one single dimension. Right. So this is feature engineering, and selection or deselection of this is feature selection. Like 2 aspects. Now, what happens with machine learning is feature extraction, feature selection. Feature extraction means feature engineering. Okay, so or you can say sometimes you extract from a different by changing it. So all that it's still under feature engineering. So the issue is when this data set is huge in terms of its parameters, to do the feature engineering becomes sort of a complex process, and in the process we may miss using certain combinations. So we may miss it. What an artificial neural network does for you is it gives you the ability of auto feature engineering, right? And it gives you the capability of learning non-linear function. A non-linear function looks very different. So let me show you what a non-linear relationship. If the relationship is linear, you can build a local algebraic function for it. But if the relationship itself is not linear. So what is it? What's the non-linear equation? Let me show you. Let me see if I can show you here. A non-linear. Okay. So this is a very big lecture, by the way. So deep learning, understanding deep learning is a very big lecture. Maybe sometimes we can have a full-blown session if you like to do that. But given the constraints of the time, so I'll not indulge you with the depth of it. Otherwise, you are looking at a very, very deep lecture. So it takes, because it's a complex subject, so it's going to take its own time. So let me just run this off. You see this, earlier we saw age and salary, and the dots were like this, okay? This is a linear relationship. You will still get some kind of linear function. But look at this. In this, we have a different problem statement. In this, we have a problem statement which looks like this. There are three set of people. All of them have headaches. There, right? Story is like this. All of them have headaches. These people were given, Dolo 650, right? You know Dolo 650. So let's suppose all of them were given Dolos. But for them, these people got Dolo 250. These people got Dolo 450. And these people got Dolo 650. Now what happened was, people who were given Dolo 250, their headache did not go. People who got Dolo 450, their headache went. Or the headache was cured. That's what, not cured. Dolo 450 headache cured. Dolo 650 again not cured. Okay, so that relationship comes up like this. Now this is not a relationship which goes like this, where you can fit a straight line here. This relationship goes like this. With time, it is not showing any particular pattern. These kind of relationships are not linear in nature, they are non-linear. For this, machine learning is it's going to become very difficult. You still can, using your support vector machines and all that. But even then, if the dimensions are very complex, then we'll not be able to do any machine learning algorithm. For example, I'll give you an example where you have a MNIST data set here. MNIST data set which is trying to something like this. Okay, we want to classify whether a certain object is a shirt or a shoe or a pant or a t-shirt or a dress or a pullover, right? So, or a bag. Now how, so all these are what? I mean, if you look at this, each of this picture for a computer is a set of pixels. Picture is a picture for us because we are intelligent beings. But for a computer, it is a fast, non-intelligent being. Okay, so it is a set of pixels which has to be highlighted. So now when you say to the machine, say, look at this pixel pattern, and I want you to remember that this is a t-shirt. Then we say, look at this pixel pattern. I want you to remember that this is a sneaker. So we are training the machine by giving all these patterns to it. And I want it to, do you think it's a machine learning problem? That because it's not just a simple linear problem that you're trying to solve between an algebra between input and output. This is much more complex. That's what that huge data set, and that's what I meant by the complexity of the data. Okay, so let's go back. Because it's a non-linear equation, non-linear relationship that you are model. That's why we eventually have to come to artificial neural networks. Okay, so here while I'm doing this, I'll also try to get you into the advanced versions of ANNs, capable non-ANNs. They are called the universal function approximator. Anyone has any doubt at this particular juncture? If there, you can stop me. There's no problem. Okay, and moving on. So there is a problem with artificial neural networks also. When the data is completely off the grid, like the data, like image recognition data, which I just showed you, then speech recognition, text pattern recognition. Then comes convolutional neural networks, where everything is stacked one other, right? So because all these images have to be seen in that dimension, right? So this CNN has its own patterns. Then comes another problem where the data has information in time, means it has to remember what happened previously to predict the future, right? So you have your spatial info there, the temporal info. Spatial info is more about how it is structured in space. Temporal info is a time series data, like a share market data, right? So at certain point it becomes like that, and every time there is a certain window which passes. For every 10 seconds input, then it goes like this. For when the gap is for 25, then the output is something else. So when there is temporal information in the data, then you want a recurrent neural network, because there is recurrence. Recurrent, it repeats in time, correct? So then the structure of that neural network changes, right? So you keep moving on like this, and eventually you end up with a data set which or you see the recurrent neural network, so correct? So now this is a recurrent neural network, and this becomes the foundation for something called transformers, right? So transformers, and eventually you will make keep giving more advanced, get this RNNs to become more advanced in terms of sequential vector models, that eventually you will bring in long short-term memories which are based on RNNs, right? So I want a long sequence of short-term memories that has to also be modern, right? So this LSTM, then comes transformers, which has its own. So these transformers eventually go, and then there is encoder, decoder models, which are a part of the transformer. That's what a transformer is, right? Encoder, decoder. Can you encode and decode the small sequences? Eventually, you see, if you go, this is how your ChatGPT works. Okay, so ChatGPT is able to do the stuff that it is able to do for you. This is how it works. So it just goes on. So maybe one of the days we can understand exactly how ChatGPT works from inside, right? So so let me go to the fun part now, as to understanding how the basic neural network itself is working, which I said we're going to go and check out the neural network playground, right? So we have all these neurons which are in front of us. This is where we're going to play around with. This is how things are going to be around. So it's quickly, we'll just set up this neural network problem. First of all, see, this is the output. These are the features. This is the input. So in fact, this is the output that I want you to learn, and input is not yet given. The input to the algorithm is this only, but it's like this. You see this? This is how the data looks like, and I want my neural network to understand and learn this data. What is the meaning of understand and learn this data? See, let me zoom in. I want it to be able to tell me the next time I put a data here. So next time I put a data here, tell me, all of you, should this data be orange in color or blue in color? Can this be a blue color data here? I put a black one, and then the machine says, no, you put a blue, then I think this is blue. Do you think if the machine says that's a blue data, will you agree with it? The machine hasn't learned yet, correct? It means the machine hasn't learned. Correct? If the machine says that yes, go ahead, give it a yellow color, or an orange color or whatever is that thing there, right? So yellow, orange. If it says it's an orange, then you'd say the machine has learned. But how is the input of this looking like? How does this look, the input? I'll show you how the input looks. It's a text, it's a table only. There's nothing big to this. There's a table. How the table looks like, the table looks like this. And I'm saying this, when given to an algorithm, looks like this. So I'm saying this is equal to this. Okay, how? I'll say, what is this point here? This point, this particular point. What is this? It is -1, comma, what is this here? Some -4.5, -4.5. Right, so -1, -4.5 is orange. Let's go and check this one. What is this? This is 2.2 or something, and this is 0.2 or something. That's it. 2.2 and 0.2 is blue. So like this, for different numbers, you have orange, orange, blue, blue, orange. So very simple. But see, this is not linear in nature, correct? It is not linear in nature. It's a non-linear data set. So I will give this feed to this, and I say, now you learn this pattern. This is your output. These are your inputs. Out of which once you set this up, your deep learning network itself will create these features. Correct? So I'll tell you, I'll explain to you what it is. So far, so good. Give me a 1 if you've understood the problem statement first. This machine has to understand this pattern now. Give me a 1 if you've understood the problem statement.
Dear participants, can you give some feedback? 1 if you understood. Write in the chat.
So what we are trying to, what is the machine trying to learn is what I'm trying to. This is a playground. This is where you understand deep learning the best. If you understood machine learning, you are now understanding deep learning. The difference is that one is a local function approximator, the other one is a universal function approximator, right? But what is that function approximation that happens? Where is that function getting stitched from? It's going to be a very complex function. But from where? Where is that function coming from? That's what we're going to see here. So I hope you've understood. I guess participants are not much. What should I call you? If you are going to participate, then we'll call you participants. Correct? If you don't participate only, how can you become participants? So, of course, thank you for other people who did participate in the beginning. But yes or no, I would like to know, like, have you understood the general gist of this problem statement? Assuming that you have, we'll move forward. Now I'm going to run this. See, I ran this and see what happened here. It understood. But while understanding, it has created these two features, x1 and x2. See, these two, and then finally you have all this neural network, and the activation function is here. It's a tangent. Okay, and then there's a learning rate, which we learned that step by step, the rate at which it learns, right? So that is your learning rate. If you don't recall, let me show you what that learning rate is. This is the learning rate, the rate at which you are learning. See the step size, slowly. That's your learning. Okay, so that learning, the activation function, regularization we learn later. Regularization is whether you're going to use a squared error or you don't use a squared error for finding the sum of squared errors. So we'll just not get into the depth of it right now, right? So activation function is the most key element in machine learning algorithm, because if I change this to linear and rerun this, so it's taking time, still not learned it. It's a linear function, but I'm using a linear activation the data itself is not a linear problem. So no matter how much time and no matter, for this, I'll have to add more layers. Let's try and see if I can add more layers, more neurons. Can we get something using linear activity? A linear step function, a linear function, a linear activation. Remember, I told you that there is a linear threshold unit. This threshold that activates the, here it was a step function, correct? So this step function is actually the activation function, right? So which function is going to be used to activate it? Is it a linear function? So I'm using a linear function, but it's not working. Okay, let me check sigmoid. It's trying all possible ways, right? Okay, if it doesn't, let's see, we can add some more features to it. Let's see if we can add some more features, and let's check it. So you see, no matter how many neurons you add, if you have the wrong activation function, you'll not converge at that. Machine will not learn. See this? How fast? 23 epoch seconds, 23 iterations. In 23 iterations, it learned. And but what happened here? Now that's what the key is. If you want to understand it intuitively, mathematically understanding it has its own, mathematically, if you want to understand it, then you have to understand this like this. Okay, mathematically, how this function I have to generate now, right? It's not a straight function which I have to generate here. It's not a function which looks like this. It's a function which looks like this. To get that, I have to stitch. I have to actually stitch a lot of curves like this. So you see this? This is an activation function which is working from inside. See? This is exactly the same thing. These neurons, inside this, there's an activation. Inside this. So this activation function in this, I think the activation function that I've used here is sigmoid. Until we could use this bent line called ReLU, rectified linear unit. So it means what? ReLU is, it will be 0 until all the values will be negative. It will start picking up once the values become positive. So it's a rectified linear unit where the more positive your input activation is, the more transfer it can do, right? So this is a simple function. Now you can use this, or we can use a softmax, which is slowly picking up, right? And in that case, we use a tanh, which again is a different function. So let's say we have a sigmoid, which didn't work, like a sigmoid curve did not work. So these are all activation functions. So eventually what I do is, what we do in deep learning is we take all these functions, this activation function, and stitch our final function. So there's a whole calculation, for this. Eventually we can eventually stitch back. See, eventually we are going to stitch and get our final function, which looks like this, the squiggle, right? This final function which looks like this. So finally we'll get that, but there's a whole process to it. Step by step we can do it, we can understand it, everything is doable, everything is understandable. So finally, see, I get this function. By stitching all these small changes for every step. So if you go here and if I start this, observe now, observe here, there's 0, and observe this. What is the weight here? 0. Initial weights are all negatives. Here there are 2 inputs. Here there are different options. What are these 2? So what these are doing is they're framing opinions. So we have how many people here now? We have 15, 16, 17, 18, 19, 20, 21, 22. Now you have 22 people here, correct, in this meeting. Now suppose we play a game. I will, and in this one, let's say I'll show you this. Let me show the screen of yours. How I'm seeing you. Here, see, I'm seeing you all here. 1, 2, 3, 4, 5, 6, 7. 7 people's names are visible to me. So let's say I want you to guess the number I have in my mind right now. I want you to guess that number. And I'll give you a hint. I have the number is between 1 and 20. Okay. Number is between 1 and 20. I want 7 of you, not the 15 others. I don't want them whom I'm not seeing. I want all these 1, 2, 3, 4, 5, 6, 7. I want 7 of you people to try to take a guess at what number I have in my mind. And I'm telling you the number is between 1 and 20. What do you think will happen? What is the chance, probability of that you will get it right? If you all talk to each other, what will you come up? You will all come up with the arrangement saying, okay, I will guess from 1 to 3. You guess from, and I'll say, if any one of you gets it right, then you win. All of you win. That's my condition. If nobody gets it right, then I win. Correct? So now what is the probability that you will actually get it right? So if you think first person, Dr. Abdul will say, I will guess from 0 to 3. And Vandana Patel will say, I'll guess from 4 to 7. And Arvind will say, I'm not able to see the whole this one. So I'll add Dr. to it. Dr. Arvind will say, I will guess from 7 to 10. Dr. Moola Banti will say, I'll guess from 9 to 11. So like that, you will divide. And now what happens is everybody now has 33% chance of getting it right. Correct? Because between 0 and 3, it can be any number. I can have any number. So you can, either you will get it right or you will get it. Somebody is going to get it right. What if I ask everybody to join in now, all the remaining 15 people? So don't you think the win probability increases? That you may guess that in fastest time. Correct? I hope you understand. So that's what I'm trying to do here. When I say I'm trying to add more layers, more hidden layers, I'm just increasing the number of people who will give me that. That is what features are, right? So I'm just increasing. So what happened here is when you look at this, see, this was the bare data given to you, correct? You see the first feature. The first feature is a guess. It's a guess. The first person, X1, is guessing. This is the input data. The first person is saying everything on the left is orange, everything on the right is blue. That is the first guess. The second person is saying, no, everything on the bottom is orange, everything on the top is blue. So somebody else now says everything in the middle is orange, everything else is outside is. So fourth guess, fifth guess is something like this. So now we want to use all of these guesses. Now I would say, I will ask this person, or now we'll say, this is my starting point, and we'll want to go and check here. Is this true? We'll give a weight to it. Okay, you are guessing this, so I'm going to give you a weight. Okay, you are guessing this, I'm going to give you a weight. But this is not enough. So what I will do is I will add more layers, and I say what we'll say, you come here and you take all these guesses. You come here to take all these guesses. You come here. So it's all interconnected. Now all of these 5 people's guess it will take, and it will come up with its own guess based on this. So like this, everybody is going to try to guess their own version. And finally, they'll come here, and then this one is, it knows, right? It knows what is the reality here. So slowly, based on their inputs, it is shaping up and asking, okay, this person is saying this person is saying this person is saying this. So this final output layer here is going to consult all these people and come up with its own guess. Now we want it we pray that this guess is almost the same guess as this. So check this out. What is happening here? Who's more right? This one or this one? This formed one option, this formed another option. See, this came out to be good. But what is happening here? This one is saying everything around is blue and everything inside is orange. But this one is saying the truth. Everything around is orange, everything is inside is blue. How did it come to this conclusion? It came to this conclusion by listening to certain people, and those people were these. So what it is going to do is, it is going to check. Let's see what it did. It gave more weightage to this, and it gave more weightage, less weightage to this. See this? More weightage. And somewhere from here it gave, somewhere from here. If you let it run the whole thing, it will see this weightage to this is a little less. Same way this one gives high weightage to this, but low weightage to something else. But these opinions were formed by these opinions. Somebody will get it right, is what I'm trying to say. See, somebody has got it right, gotten it right here only. And these also got right, this also got right. Here already there. The second guess only and second layer only this was, but it had to be transferred to get here. So this is a whole network of a big gambling. And all this gambling is based on the same activation function, TANH, which is there in every neuron. Everybody is going to get activated for the same function, but the input levels will be different. So we are going to take what happens is, for this value, the activation changes something like this. And for this value, the activation changes something like this. For this, we are going to stitch all, because this is also a function, this is also a function, this is also a function. Correct? TANH is its own function. If you go and check a TANH function, it's a function of y and x, but and something more, right? So everything is a xy function, and based on who got the highest weightage at every level, let's suppose this, and this, right? And who influenced this and this would have influenced this. So this is an input, but here your function starts from here. So this into this, to this, to this, and to this. These are the ones which would finally become the model, the equation. It will be an equation which looks like this. Plus or minus 7, whatever. Just giving an example. So finally, you have figured a way out to model a nonlinear function. So same way, let's say I take a very complex equation like this. Now this was the simplest equation, simplest data set. I'm going to take a complex data set and let's run this for the same value. It's not able to. So in this case, I want more features, and probably I might get away with same levels. Right, so probably I might converge. It's going to take some time, but eventually it's going to converge. Tried its best, but couldn't. Still trying. Overfitting sometimes, underfitting sometimes. But just the change of activation function to value okay, maybe I have a few more. So this is what happens in your deep learning problem. So why you add more layers? So that you can increase the number of guesses. Looks nice. It's almost getting there. So I'll leave this exercise to you. Okay, what are you going to do? What else? I can add more input neurons here. Try and see, add more hidden layers of maximum hidden layers. You can add more neurons. Try and see whether you can change something here. Regularization, L1 or L2, right? Regularization rate is 0 right now. So try and see if you can change this, and you'll see that you'll actually get a perfect model. So I guess when you do that activity, you will have more motivation to go and learn what these stuff actually does. So I think we are at the end of the session. So I had thought about a 90-minute session, but of course, things. Am I audible? Or
Yes, sir. Yes.
okay. So I guess. So I'll stop sharing the screen right now, and I'll take any questions if anyone wants to ask any questions.
So participants, if you have any question, you can ask directly. You can simply unmute and ask. I think there is no question.
I think I've done a very good job by making it so clear that everybody understands everything now. Is that the truth? So yeah. Feature extraction. In this feature extraction, there is a feature. These are all features, and out of this, when you look at this given data, you want to give this input hypothesis to it. So suppose what would you do? Okay, let's say this is feature extraction. So you got a feature, you created a feature, then out of this you created new. So this one is x1 into x2. This is a dot product actually. Dot product of x1 and x2 gives you this. Then you decide to go and do sine of x1, which gives you this. Okay, this is the extraction of a feature. You have extracted a new feature from an old feature. That is feature engineering. Okay, so feature extraction, extract a feature which wasn't there. It never looked like a combination of this could become its own feature. See, you see this. I have not created anything. These were two simple starting points. Starting points was what? X1, where everything on the left is orange, everything on the right is blue. X2, everything on the top is blue, everything on the bottom is orange. Next, what I did x of 1, 2. Okay, so we got a transform. What we do? This one. We transpose x1 on 2 and we get this, and 2 on 2 we get this. Then what we do is, I think this is x1 square, x2 square power. Okay, so you got an x1 square, you got a new feature extracted. X2 square, you got a new feature extracted. Then you say what we can do x1 and x2, you got a new feature extracted. Then is a sine of x1 is a new feature, sine of x2. You can go ahead and add more. You can add cos of it or some other thing. You can have x1 into 2x2. That can be a feature, right? You'll never know which feature is going to add. That's the the art, right? So here in this case, what happens when you really do deep learning, this automatically is taken care of. You don't have to do. You have to just set it up and show the output, show the input and output. This feature extraction, it will only do. Okay, we'll never know which feature it will, how it saw, how it learned. We'll never know, but we'll get the perfect model. That's what feature extraction is. Here manually I'm doing, or it was set up for us in machine learning. In deep learning, it will do its own feature engineering, and because you have given the ultimatum to it, like, or the agenda, boss, I want you to learn this, do whatever you want with the input data. Sir, I'll just try every different way of getting you the model. So it will iterate. That's how. So I hope it's sort of making sense. What is regularized? If the data is so, the answer to the question here is by Kara Shiva. Even many neurons may give wrong assumptions in that case. Eventually, if the data is very, very complex, you will get wrong model. You can't help it. You can only have to, ChatGPT also will hallucinate sometime. It's not perfect, right? So even despite being trained on such high-level models, you can face that. So it's one-off thing that will happen. Because you can only have. That's why the accuracy. Many neurons may give wrong assumptions, and in which case wrong prediction. So out of 100 problems, you may get right 95 or 96% of the time, which is okay. 100% if nothing will be good. 100% model prediction, no model can give. So yeah, so you may have a wrong. So that is a possibility. And what is the regularization element and how it helps in training the model? So basically, regularization is whether you want to take a sum of squared errors or whether you don't want to take a sum of squared errors. So I was just trying to show you this. So I was showing you that this line. So this line was there, so it was moving, right? So every time it moves, there's a new value which comes up here, right? So here, when you're trying to, at this level, you want to take how far is this from the actual hypothesis. So what do? You take the square, you first find the distance between this. Then you square it and add it up. So it becomes sum of squared errors. Or it can just be sum of errors. So by squaring it, you have removed the negative distances. Like from here, if you say this is negative and this is positive. So if you just take the squared errors instead of sum of squared errors, then you are adding a new dimension to it. If you take squared errors, I'm sorry, this is sum of errors, sum of squared errors. Okay. So if you don't square it and add it, you may have a chance of negating many. So if you think the linear relationship or relationship is in such a way that you're just by squaring the errors, if you can drop off many other data, many other assumptions that are in the data, then you may find yourself. So you have to just check, and you have to use both of them. It's not like you know before only whether you want to use a sum of squared errors or. So L1 regularization is SSE, L2 is SE. So that's what it is. So it takes a bit of time. Here it has a longer explanation. But I'll do one thing. I'll send you a video. There's a video that we have created of what is exact difference. So I'll probably share that video so that we will explain. Otherwise, it will take a long time for me to stand up from there and get it. Next question. What is the question? Is it novelty in DL algorithm? What is novelty in DL algorithm? They read the Reddy explanation. What is that you're asking? Is it novelty in DL algorithm? Which one? Feature extraction. No, machine learning means, what is the meaning of novelty? Novelty means something new in this one, right? That's what I'm understanding. The meaning of novelty that you're saying is that it's new in deep learning. It is not in machine learning. Is that what you want to ask me? Is that what you wanted to ask me? By novelty, does it mean that is it a feature of deep learning and can it not be used in machine learning? It can be used in machine learning. In machine learning, you have to manually do the feature engineering. In deep learning, automatically it will do, and won't even tell you what it did. At least in machine learning, we are the ones who did the combination. We know what combination worked. In deep learning, it will only do, because until it learns it, it won't leave. So it will do its best, all possible combinations, because it's a machine, right? It's a very powerful machine. So that's why you have GPUs. So that's what the TensorFlow is. So why it is called a playground of TensorFlow playground? Because TensorFlows are, all the tensors are graphical processing units. So it's all very complex, very hard, high-speed processing units. So it doesn't matter. It will probably do all kinds of feature extraction and feature engineering for you. Right. ReLU is preferred because it's the nature of it is like that. ReLU is more like, if you see the ReLU is for f of 0, it is 0. For f of 1, it is 1. That is what ReLU is. If you see in terms of this one, it's like this. So when you have multi-class problem, there are multiple classes, and it has to distinctly identify what are the features which makes the output as this class, or input belonging to this class. What other features are there which makes, so you don't give it any in between states. You say 0, 0. If you get one, activate. If you get a feature, if you see a distinctive feature, activate. So when there are multiple classes with ReLU as a function, internally you are giving a very strict guidance to the machine learning algorithm, saying you activate only, because otherwise what happens is, for a certain small change, it may say, okay, it belongs to this class also, it belongs to that class also, right? So that doesn't work, right? So that's what, when you have a function like this, softmax, you're saying we are giving all this extra, even if it is not there, you're giving that extra feature to it. So what will happen is it will fail. It will fail in classification, and it will have a lot of misclassifications. But ReLU works well because it's strict. It's a 0, 0, 1, 1. If it is 0, no activation. If it is 1, start activating depending on the weights given to it. So weight factor gets multiplied over the system. That's how it works. Thank you. Right. So anyone else has any question or like to post session? If we can close the session, I think it's already lost the time barrier.
Yeah. Okay, sir. Thank you, sir, for taking your time for explaining everything from the very basic to the advanced level, and I'm confident that everybody will be benefited. And okay, thank you so much, sir.
Thank you so much. Thank you all. I would like to just because of course now for us it's because we run an institute also. We have two companies. One is Analogika, one is institute called CertiShort, which is pretty famous in Bangalore. People come here to get advanced certification, get placed in as an ML scientist and all. So I have my just I want to share. Okay, I'm just going to share my link. Just hopefully, if you liked or if you like what you learned, or you know, just please go to that link and drop us a rating or a review or some feedback. That will really help us. So yeah, hopefully we can sign off with that. Good note. Thank you all. Take care. Any other thing that you want, sir, can contact me for videos or any other explanation. I'll be more than happy.
Sure, sir. Thank you.
Thank you so much.
Participant, you can give feedback and quick feedback on the link sir has shared.